Welcome to the Explainer. Today, we're going to peel back the layers on the AI systems we use every single day to look at a hidden battleground. We are talking about adversarial machine learning, or what's really the critical field of security for AI.
And look, that's not just some line to get your attention, it's a fundamental truth. The very machine learning models that are designed to help us, from identifying photos to spotting threats, they have these hidden vulnerabilities that can be exploited in really surprising ways.
So here's our game plan. We'll kick things off by figuring out what security for AI even means. Then, we're going to dive into 3 major ways attackers can break these systems: by poisoning the data, by evading the model, and by straight up stealing its secrets. After that, we'll look at how we fight back, and why this whole thing has become a constant, never-ending arms race.
Right, so you often hear about using AI for security, like an AI that sniffs out malware. But today, we are flipping that script entirely. We're talking about the security we need for the AI itself. This is the absolute core of it. It's all about protecting these complex models from deliberate attacks. You can think of it like digital self-defense for the brain of the whole operation, making sure the AI can't be tricked or turned against us.
Now, to really get this fight, you first have to ask, what does the attacker actually know? In what we call a white box attack, they have the full blueprints, everything. But way more common, and frankly more realistic, is the black box attack. Here, the AI is like a sealed box. The attacker can't see inside, but they can poke it, send it inputs, and watch what comes out, trying to figure out how to crack it from the outside.
Okay, let's get into our first major attack vector: poisoning. This is pure sabotage, and it happens before the AI is even out in the world, by corrupting it during its most vulnerable phase, training.
So imagine an AI is learning to identify cars by looking at a million pictures of cars. A poisoning attack is like someone secretly sneaking in a few hundred pictures of motorcycles, but labeling them all car. You're basically contaminating the well of data the AI is drinking from, building a hidden flaw into its logic that's just waiting to be triggered later.
So how does this actually work? A classic example is called a Trojan attack. An attacker creates some kind of subtle trigger. It could be a tiny, harmless-looking sticker or digital watermark. They add this trigger to some of the training images and then inject this poison data into the training set. The model, trying to learn, makes a secret, wrong connection. It learns that whenever it sees that specific trigger, it should make a specific wrong decision. It's a hidden backdoor, programmed right into the AI's mind.
All right, that brings us to our next major threat: evasion. Now, if poisoning is sabotage that happens during training, evasion is a real-time deception. The AI is already built, it's live, it's working, but an attacker finds a way to fool it. And this is the most common kind of attack you'll see out in the real world.
The key thing to understand here is that the AI model itself isn't broken or poisoned. It's perfectly fine. Instead, the attacker creates a special kind of input, what we call an adversarial example. Think of it like a master of disguise, or a perfect optical illusion that's designed specifically to trick a machine's perception.
So just how subtle can this be? Well, let's take a look at a famous example from an attack called Deep Fool. We start with a normal picture of a Canon camera. The AI knows exactly what it is. But could an attacker make it see something totally different?
As you'd expect, we feed the original image to the model, and boom, it gets it right. Prediction, Canon. It's confident, it's correct, everything is working exactly the way it's supposed to.
But now, watch this. The attacker makes a tiny, mathematically calculated change to that image. I'm talking about a change so small, it's often completely imperceptible to the human eye. We feed this new image to the exact same AI, and suddenly, its prediction is a projector. The model has been totally fooled, and it shows you just how fragile that confidence can be.
Okay, our third type of attack is one that hits close to home for every single one of us: privacy. The goal here isn't just to trick an AI. It's to make it cough up sensitive information it was never, ever supposed to share.
Yeah, with these attacks, the whole point is to infer secrets just by watching how the model behaves. This could be information about the private data it was trained on, or it could even be the secret sauce of the model itself. We're talking about confidential, valuable, and sometimes
deeply personal information.
And this is exactly why it matters to you. A membership inference attack could be used to figure out if your specific medical record was part of the dataset that trained a hospital's AI. Feature inference could steal specific details about that data. And model extraction, well, that's just pure corporate espionage, rebuilding a competitor's secret proprietary model, like the one a bank uses to decide who gets a loan.
Okay, so after seeing all those attacks, it can feel a little daunting, right? But for every move an attacker makes, you better believe the defenders are working on a countermove. Researchers and engineers are in this constant battle, coming up with clever ways to protect these systems.
And the defenses are actually tailored to the specific attack. To stop a poisoning attack, you have to inspect the data for anomalies before it ever gets to the model. To fight back against those real-time evasion attacks, you can use something called adversarial training. And to stop privacy leaks, you rely on powerful techniques like anonymization and differential privacy.
Let's just zoom in on one of those for a second. Adversarial training. It's a pretty brilliant idea, actually. You basically fight fire with fire. You generate a ton of those tricky adversarial examples yourself, and then you show them to your model while it's training. You're teaching it, hey, this is what an attack looks like. Don't fall for it. But this extra strength comes with a really interesting trade-off.
And here is that trade-off in action. A standard, regular model is super accurate on normal data. Here it has just a 3% error rate. But the adversarially trained model, the one that's much tougher against attacks, becomes a little less accurate on that same clean data. Its error rate goes up to 7%. This shows a fundamental tension in AI security. Making an AI more robust can mean making it a little worse at its main job. It's a constant balancing act.
So all of this leads to the biggest question of all. Why is this so hard? I mean, if we know about all of these vulnerabilities, why can't we just, fix them? Well, the answer really lies in the fundamental nature of AI itself. Honestly, the biggest reason is just the mind-boggling complexity of these models. They create these weird little edge cases, what experts call low-probability pockets, that the AI never saw during training. But a clever attacker can hunt for these pockets and exploit them. On top of that, our debugging tools are still pretty limited, testing new defenses is really slow, and a lot of the attacks we see are cooked up in a lab, which isn't quite the same as the messy real world.
So as we build more and more of our world on these foundations of artificial intelligence, in our hospitals, in our banks, in our cars, this secret war happening inside the machine suddenly becomes everyone's concern. And it leaves us with a really critical question for our future. In this new world, how do we decide who and what we can actually trust?